Okay. So we have seen the computer tomography, and we saw that there is an analytical way of doing things. One of them is by the Fourier technique. The other one is by direct filtering. But all of these processes are known as back projection, because we are back projecting from our observations to the signal domain or the image domain. The last one, which was the Radon's inversion, was it's also known as filter back projection algorithm, because we are essentially filtering with 1 over t, or the derivative of 1 over t. Anyway, so the next thing that we can discuss is, let me open a new page for that, is using algebraic methods. Where the optimization by projection onto convex sets is one algebraic technique that we will see, which the projections onto convex sets is abbreviated as this, POX, projections onto convex sets. Now, that convex set is usually a constraint. It's usually an information that you already know. And it's weird or sometimes interesting for the student to actually come up with an idea that the constraint or the observation makes a convex set. What makes a convex set? That's a critical thing. But as we see more and more examples, you will understand what we really mean by having a convex set or a convex constraint. Now let's start with the CT example. And for this one, we may start from a trivial example of an image consisting of only 4 pixels. And these 4 pixels are, let's say, A, B, C, D. And we want to reconstruct what is ABCD from the X-ray projections. It's not the projections that we're talking about in POX. That's a different projection I'm talking about. It's this projection, I mean, which actually gives you A plus B, okay, is equal to, let's say, 3. And here C plus D is, let's say, 8. So from these two observations, or from this observation, giving you 2 sample points, is it possible to resolve what is A, B, what is B, etc.? No, of course not. So how many more projections do we need? We need 1 more projection, which will give you 2 more observations. For example, maybe these, like A plus C is equal to 5, and B plus D is equal to 6. I'm just inventing numbers here. They're not important. But overall, it makes some number of equations. Like A plus B is equal to 3 is an equation, for example. So how many equations do we have with these 2 angle of projections? We have 4 equations. And we are trying to resolve for 4 distinct values, namely A, B, C, and D, which is possible. So we just solve this set of equations, and we find individually what is A, what is B, what is C, what is D. You can just do it. But when we try to do it, essentially it comes out to be in the form of this kind of a matrix equation. It's like we have A, B, C, and D here, and we have 1, 1, 0, 0, which makes A plus B at its result. And this is the resulting numbers. 3, A plus B is equal to 3, and C plus D is equal to 8. A plus C, oops, I'm very uncomfortable with this, sorry. A plus C is equal to 5, and B plus D is equal to 6. So in general, from linear algebra, we know that the way to solve this set of equations is saying that this is a matrix. We can call this unknown vector an x vector, and this observation could be named y vector, for example. Then a times x is equal to y, and therefore x is equal to a inverse times y. So this is the way to solve, at least theoretically, to solve the linear set of equations. But of course, as you see, it is becoming huge if the number of unknown parameters grow. For example, let's think of a very small CT image, which is 1000 by 1000, only a mere 1 megapixel. Even the telephones are like 100 megapixels photo taking apparatus. But these are, let's say, small, okay? 1000 by 1000, 1 megapixel. The size of A will be what? It will be, can you tell me? I'm expecting an answer from you students. If it's a 1 megapixel situation with 1 million pixels, how many equations are necessary to solve for at least? So A has a size of what by what? I'm asking you guys now, and I'm expecting an answer. It may be wrong, but whatever it is, I'm expecting an answer. Ezgi, are you there? Or maybe the students are not there, or Ozan, yeah.
Aynı sayıda.
Yeah, say it again. So I'm asking you this question. We have 1 megapixel image, 1000 by 1000. So what is the size of A? What by what? That was my question. And you say it's the same, for example, 1000 by 1000. Did you say that? Was it that? Was that your answer?
1 million equation.
Yeah, 1 million equations. But what is the size of A? That is my question. A is a matrix. What by what?
1000 by 1000.
1000 by 1000. Yeah, that is the wrong answer, because I want you guys to think of it and come up with the wrong answer. No, it's not 1000 by 1000. It is actually 1 million by 1 million. Look at this case. It is a 2 by 2 image. It's not 1000 by 1000. It's 2 by 2. But A matrix becomes 4 by 4 because there are 4 pixels. So A is 4 by 4. If it is 1000 by 1000, there are 1 million pixels making 1 million equations. So A becomes 1 million by 1 million. And there are 1 million unknowns. The X vector consists of 1 million pixel values whose values we don't know. All right, so it will be a 1 million by 1 million A, and you simply cannot invert. Okay, you cannot really take the inverse of a 1 million by 1 million matrix. So this thing is quite inappropriate. It needs elaboration. The way that for larger pixels or for larger images, it's just an extension of this. So we have a huge image, and it's consisting of grids making pixels. So at every angle, we are just adding this pixel, maybe within even some scales, okay? It's not really just exactly equal to 1. It's not A plus B, but it may be A plus 0.3 times B plus 0.7 times C, etc. along this path, depending on how much the ray is passing through every grid, every square grid. So some from here, some from here. So these pixels are all added and their summation comes out from here. And of course, the others. And overall, the situation becomes like a huge set of equations, which is notated as, which can be notated as G of S sub m, comma, theta sub n. I didn't put theta in the subscript of G. Actually, this is G theta of S I'm trying to say. So this is G theta of S I'm writing. But the subscript of theta also has a subscript of n, which is essentially an index of theta. So in order not to confuse, I write it like this, is equal to, let's say, I from 1 to capital I, which is the size of the image in horizontal direction maybe, or vertical, and j from 1 to capital J, and Fij is the pixel value times, now this is the sampling line equation I'm trying to talk about, Hij. This is the line equation corresponding to a shift of S and the rotation angle of theta. This is a discretized version of the double integral that I wrote in the beginning of the previous hour, okay? Previously, it was in the form of an integral. Now I'm trying to discretize it and write it like a discrete summation because that's what we have. But this thing makes a G matrix, since it's matrix, no, it's a G vector, it's not a matrix. Although it has two parameters, S and theta, I'm just stacking those entities for every variation of S and theta to form a huge vector of G. That vector length is 1 million, by the way, is equal to this matrix, the H matrix, which is 1 million by 1 million, at least, by the way. It may be even more than that, because it may be, the number of equations may be more than the number of unknowns, which you have to solve for the least square solution in that case. And this F is just the pixels that you are looking for. So G is your observations, H is your line equations, discretized line equations, and F is the image that you're looking for. And if you simply say that F is equal to H inverse times G, that is where you are doomed, because this G is P by 1, where P is equal to M times N. M is the number of shifts along the S-axis. So the S resolution is your is determining your M. It may be very dense. So M is a large number, like at least 1,000, maybe more than that. N, on the other hand, is the variation of angles. How many angles can you have? Maybe again 1,000. So this will make like 1,000 times 1,000. So that's 1 million. And the others, F, for example, is Q by 1 length vector, where Q is equal to I times J. And I and J are here. They are the pixel sizes, horizontally and vertically. So this is, again, approximately 1000 times 1000, again 1 million. So that makes H to be what by what? I'm trying to estimate here. It's, I think, P by Q. Yeah, P by Q times Q by 1 will give you P by 1. So H is P by Q, which is approximately 1 million by 1 million. Okay, these are the sizes. So it's not feasible. But if you think of these as a set of equations, every row of that equation or every row of this vector matrix equation will actually give you something like this. For instance, it will give you the first element of G, let's call it G1, the first the entity in the G vector is equal to like H11 times F1 plus H12 times F2 plus H13 times F3 plus all the way up to H1Q times FQ. And G2 will be equal to H21 F1 plus H22 F2 plus H23 F3 plus all the way up to H2Q times FQ. And it goes on like this. And they are all line equations because it's where the name linear set of equation comes from, linear. So there's that every equation is a line. It's a linear equation. Although I have only a two-dimensional surface to illustrate, to draw, essentially these equations, G1 is equal to this, G2 is equal to that, etc., they make lines. For example, this is a line. This is a line corresponding to the first equation. Equation 1 gives me this line. But it's actually a q-dimensional space line. It's a line on the q-dimensional space. And G2 is equal to blah, blah will give you another line, equation 2, again on the q-dimensional space, but they intersect, okay, at a degree of freedom. I cannot really say that that point is exactly one single point on the q-dimensional place, but it's an intersection of within hyper surfaces, let me say it like that. Then you have another line, and oops, this one was bad, sorry. And other lines. These are all equations which all have only one intersection point. And that intersection point here corresponds to the solution of F1, F2, F3 up to FQ on the q-dimensional space. So we are looking for the intersection of these lines. How can we find them? Now, here comes at last the projections onto convex sets concept. We start from any arbitrary f value. F1 is equal to something, F2 is equal to something. It's like an arbitrary, a random image that we start with, which may be on the q-dimensional image space, which may be a point here, okay? So when you take the projection of that point on the first line, you can do that because equation 1, for example, is a line equation and lines are convex sets. It's possible to make an orthogonal to projection to this line. It's 90 degrees onto the line, and that's possible. You can always do that. The question you must ask is about the rigorous definition of a convex entity or a convex set. So what is it? Let me briefly mention about that. If you have 2 points within the convex set, let's say one of them is x1, the other one is x2, okay? Then lambda times x1 plus 1 minus lambda times x2 will be an element of the set, will be inside the convex set for lambda between 0 and 1. Okay, let me make it a little bit larger here. So for lambda between 0 and 1, lambda times x1 plus 1 minus lambda times x2 must be within the set. Usually the situation is like this. This doesn't really look like a convex set, but let me draw something, a counterexample, which is not a convex set. Okay, this one. For every 2 point that you must choose, you may choose x1 and x2. It means everything that connects the straight line between x1 and x2 must be within the set, must stay within the set. That's what lambda times x1 plus 1 minus lambda times x2 means. For example, you choose x1 here and x2 here, and you connect them with a straight line, and every point along this straight line must be inside the set, the defined set. Is this like that? No, this one is not convex. Because, as you see, this portion stays out. Convex sets are, as the name suggests, convex. They are, their curvature is always outwards at every boundary. Now, lines are convex. So this line it's always a convex entity, a line. Because if you choose a point x1 and if you choose another point x2, then every point in between will still be inside the line. So it's convex. A rectangle is a convex. A circle, an ellipse is a convex entity or a set. A line is therefore also a convex set. That's why when I make a projection to a line, the projection outcome will be deterministic. There is no ambiguity. There are no two equal alternatives of distances. For example, here you may have a point whose distance to here is minimum, but it's the same as the distance to here. They both look like the same distance from that point. And so the projection is ambiguous. Which one should I choose for the projection? The orthogonal projection means finding the minimum distance from you to the set. Finding the minimum distance point on the set will be the orthogonal projection. Now, after the projection, you come here, which obeys with the equation number 1. Then from here, you make a projection to equation 2, for instance, again, an orthogonal projection. Now you obey equation 2, but obviously you don't obey equation 1, but you are closer to the intersection point in terms of the Euclidean distance. And then you make a projection to here, to the third equation, then the fourth equation, then the fifth equation, the sixth equation, then maybe back to equation 2, then maybe back to the previous fourth equation, etc. So with these projections, you approach to the intersection point. So by making iterative projections onto these equations, you will hopefully quickly converge to the center position, the intersection position. That is the strength, it is the power of alternating projections. I said alternating. Now that alternation is a good way to improve the speed of the convergence, because equation 1 and 2 may be, they are linearly independent, of course, but they may be too much aligned. The angle between the two equations may be small. So a projection from equation 1 to equation 2 may not be a very good idea, because if the angle is too low, then the projection will make very little improvement. But if you project equation 1, for example, to equation 4 immediately, that will be a dramatic improvement. So we tend to, this is a numerical way of solving things, we tend to alternate the projections from 1 to n, from n to m, m to p, p to q, q to n, etc. Then it will probably faster converge to the true intersection. So if you have more than 2 sets, I think the projection ordering should be shuffled. It may not be enough within one projection loop, that is within 1 million iterations. You will probably not reach to the intersection point close enough. So you will have to make 1 million more projections and then 1 million more projections. You may think that, well, millions of projections, this also looks a little bit computationally expensive, but it's not, because every projection is a very simple linear algebraic inner product way of doing things. It's like this. It's the next point, let's say f p minus 1 solution is equal to the previous solution fp plus g, one of these g's, let's say gp minus or gp plus 1, let's say hp plus 1 inner product with fp divided by hp plus 1's square norm times hp. You may try to understand what I'm doing here, but it's just a normalization of hp, okay? So this is the numerator, the denominator are just the normalized h values. You can just evaluate them for once and then keep the normalized things. It's like these line equations, but the vectors having unit norms only, which is a one-shot, a single-shot operation. And the numerator has a subtraction between two vectors, and the right-hand sided vector is just an inner product. And the inner products are not as complicated as taking the transforms or taking the Fourier transforms, basically. So, or filtering. So this is an easier way to approach. And sometimes, so even for solving these computer tomography business, it's possible to split your problem into linear equations, line equations, and then make projections onto those line equations. Hopefully you will quickly converge to the intersection, which will give you f, which is the image that you're looking for. But computer tomography is not the only thing that you can do using POCs. POCs is also a very popular method, and it's your like only hope for even some problems where you can do nothing more. You only have the constraints. So if you have constraints, each constraint will define a set, because some solutions will be compatible with the constraints, some will not comply with the constraint. So constraints will be like this. And some of them may be your observations. So one of these sets may be your observation. The other sets are your constraints. So you start from an observation, which is here, and then you make an orthogonal projection to one of the constraints, and you come here. Then you make a projection to one of the constraints, and you come here. Then you go to the other constraint and come here. Then this constraint come here, etc. And you will, eventually converge to the intersection, which is the point that satisfies both of the constraints and the observation. It is still inside the observation space. That is the thing that you're trying to go into. It may be a blurry image, for instance, and you want to de-blur it. You want to come up with a sharper image. Now let me give you a few examples of constraint optimization, or POX examples. One example we can think of is, what can it be? Okay, here is a good one. Suppose that you have an imaging system which gives you an image, let's call it X, but the image only consists of the angle terms, and the magnitude or the phase terms are available to you, but the magnitude is lost. How can it happen? It is actually essentially happening all the time inside sensors. The sensors are sensitive to differences, differentials, and the difference is essentially the angle of the Fourier transform. So X has the angle of, let's not call it X, it's the observation, let's call it A, okay? So you observe A, which is the angle of X. What do we mean by this? It's essentially X has a Fourier transform, X of X and Y. So the coordinates and the name of the variable also mixes with one another, sorry about that. And the Fourier transform of it is capital X, okay? Capital X is containing complex numbers, and the complex numbers have one magnitude and one, no, it's not like this, one angle. So that X is essentially magnitude of X times e to the j angle of X, okay? So I'm not splitting into real and imaginary parts, but I'm splitting into magnitude and angle for the complex number X. So magically, somehow, you only have, oops, I think I made a mistake here. It's e to the j times angle of X, I have to write. So somehow you only have this, the angle of X, and this is lost. Your sensor is unable to depict that one. You can create some toy examples. Maybe I will ask this kind of a question in your final midterm, in the take-home, and I will ask you to write a MATLAB or whatever language you may wish, a program to write this iteration, okay, that I will describe. The iteration starts with the angle. How can you do that? You may, for instance, take an image, let's say the cameraman image, which is a very standard MATLAB test image. You start with it, you take the two-dimensional Fourier transform of it, and you express it in polar forms. You find the magnitude of that Fourier transform and the angle of that Fourier transform using the appropriate commands of MATLAB or Python or whatever. So you only have this. You start from there. And you want to reconstruct the image. So initially you only have the phase of the Fourier transform and I'm asking you what is the image. You start with a point where you at stage 1 you say that magnitude of x is equal to 1 for all pixels. It's just 1. So we don't know the magnitude of the Fourier transform. I'm assuming that it's 1. It's a point on the Fourier or time domain. Fourier and time domain are analogous to one another because we don't really, they can be convertible to one another. So this is your initial estimate or guess of your image, only consisting of the phase of the Fourier transform. And the magnitude is just constant 1. Where can I project this? What is a projection that you may think of and propose? Those are the side information that you must think of. They may be observed things, or they may be naturally, some natural constraints where you must think of. The thing that I tend to think are two constraint sets, and they are convex. They are convex sets. So in the next step, I project to the first one of them, which is telling me that I reconstruct x as magnitude of x, which is all ones initially, times e to the j angle of x, which are the observations that you have, and take the inverse Fourier transform of x and say that it is xi. The projection, I didn't take the projection yet. I didn't have the projection. I just converted everything into time domain now. And in the time domain, I do the projection now. Xi prime is equal to the real part of xi. What is this projection? What does it make? It must have two conditions. One of them is this projection must define a set that must be convex. And second, this must be the orthogonal projection to that convex set. So my convex set is the following. Set is defined as set of real valued images. So my image is real valued. It has real values. But when I take the inverse Fourier transform of capital X, with magnitudes all being ones and phase being the observation, when I take the inverse Fourier transform of that, it gives me an inverse Fourier transform which is complex. It's not real. But my set now is the set of real valued images. It's this set, let's say. Of course, it's an infinite set, but nevertheless, it's a set like this. Is it complex? Is it convex? Is the first question that you must answer. So inside the set of real valued images, if you have a real valued image here, image 1, let's say, and if you have another real valued image, image 2 here, if you take their average images, some from image 1, some from image 2, and make a blend of those real valued images by lambda and 1 minus lambda, will the blended image be real valued or not? And the answer is, of course, or everything. If image 1 is real, when I multiply it with lambda, if image 2 is real, when I multiply it with 1 minus lambda, they will all be real. And when I add them, it will be real. So yes, set of real valued images is a convex set. Interesting, isn't it? It's not like the algebraic sets that we have, but it's a verbal way of expressing a constraint and saying that it makes a convex set of real images. And because of that, I make this projection. Now, the next question is this an orthogonal projection? When I take the real part of a complex, so here we have a complex image now. When I take the real part of that image, will it be the orthogonal projection, and will it give me this? this is the shortest distance solution, which stays inside the set, but it is nearest to the starting point value, which is xi, okay? So what is a real number which is closest to xi? What's the answer to that? The answer is the real part of xi. If you just eliminate the imaginary part, assign it to be 0, so the distance between xi prime and xi is minimum. Because if you choose another real value, which is not the real part of xi, then the distance between xi prime and xi will be even more. For example, what is the nearest real value? So this is an example. What is the closest real value or real value to a complex number, let's say 5 plus 3j. So tell me the real value which is closest to 5 plus 3j. It must be real, and the difference, Euclidean distance between 5 plus 3j and that real number must be minimum. That must be the smallest. And the answer is 5, the real part. If you say 6, the difference between 6 and 5 plus 3j is more than the distance between 5 and 5 plus 3j, obviously. Okay, so taking the real part is an orthogonal projection. Look at that. It doesn't have the linear algebraic formula that we have developed before, which was this red formula here. It's not really like that, but you have to imagine and you have to come up with a solution. In the third step, I do another projection. The projection is the following. The value of the image pixels must be between 0 and 255, or between 0 and 1, whatever. I put a lower limit and an upper limit to the real values as well. How do I do that? First of all, is this a convex set? If the pixel is between 0 and 255, let's say that the pixel value is 10, and the other pixel value that we will draw the line between, or blend these two pixel values, one of them is 10, the other one is 100. So everything between 10 and 100, will they be between 0 and 255? Will it be in this range? Of course, obviously, right? So every image with pixel values between 0 and 255 will make a convex set, because their blends will also be having pixel values between 0 and 255. So this is convex. And then I have to find the orthogonal projection. The orthogonal projection is to find the smallest distance image which obeys this. And the operation, or the projection operation, is to chop beyond 0 and 255. So if the pixel value, the real value that you get from step 2 is less than 0, for example, you assign it to be 0. If it is -5, you say it's 0. If it is 300, you say it's 255. So you chop anything beyond as well. And if it is between 0 and 255, it is inside the set. You don't do anything to those pixels. So cropping or chopping the pixel values beyond these to those boundaries, clipping to those boundaries, is the projection. Is it an orthogonal projection? Yes, because this is the set 0 to 255. This range is the set, so it starts at 0 and ends at 255, and you are at, let's say, -5. So what is the nearest point in the set which is closest to -5? That is 0. What is the closest point to 300 within the set? It is 255. Okay, so chopping is the orthogonal projection. If you chop -5 to, let's say, 10, what's the difference between 10 and -5? It is 15. It is more than the difference between -5 and 0, which is only 5. So that's why you are only chopping until the boundary. So the values must be between 0 and 255 is the third projection that you make. And then the fourth projection, it's not the third projection, it's the second projection. The third projection is the original condition. At step 4, you take the Fourier transform and assign the angle of x to be the observation. Now, this is our starting point. We take the Fourier transform of it. Now the magnitudes are something, they have some values, and the angles are also changed. They change to some amount. Now I replace all those angles. I drop all the angles from my Fourier transform after I take the Fourier transform. Let's say I have y, which becomes magnitude of y times e to the j angle of y. And I replace this with magnitude of y. I keep the magnitudes, but I replace the angle with the angle of x that I was observing. So I change the angles back to the original observation. Now, is the set of images with, let me write it, is the set of images, that's miserable, sorry, is a set of images with phase equal to angle of x, a convex set? Now that's a good question, because I'm telling that by this replacement, I'm making a projection onto this set. So it must be convex, and furthermore, plus this replacement must also be an orthogonal projection. Is this a convex set? And the answer is yes. If you have two images, one of them x with angle x, and the other one is y with angle, again, x. If you blend x and y by multiplying the first one with lambda, the second one with 1 minus lambda, okay, you blend them, their angles will also be blended in a similar way, and the angle of the blend will also be angle of x. Okay, so the set of images, all with the same angle term, angle of x, when you blend them, you will always get the angle of x. So that's why it's a convex set. Their blends will always give the same angle. So it is a convex set. Now, honestly speaking, when I ask a question in an examination, and if you think of a set for the reconstruction, I can think of 3 sets here. One of them is the set of all images with angle x, and one of them is the solution. And the other set is all the real valued images, which is a very good assumption because the values of image pixels are real values. And the third one is putting a bound between plus and minus something, or between 0 and some upper bound. That's also a reasonable thing. We don't have infinitely bright or negatively bright pixel values, clearly. So these 3 sets. So in your while answering your questions, you will have to come up with these sets, which is difficult enough, but not enough. You have to show me that they are convex with rigorous and at least reasonable proofs. I'm not giving you proofs right now. I'm just motivating or giving you impressions that they are correct. But in an answer sheet of your exam papers, I would expect some better way of putting these things and illustrating that these sets are indeed convex. And then replacement of the angle from this to this is the orthogonal projection, because it's the shortest projection. This one, y prime, let's say, is in the set of images with angle equals the angle of x, and it is the nearest to y. So the distance between these two is the minimum. If you of course, you have to replace the phase, the angle term. This replacement is necessary, but do not touch the magnitudes. Don't do anything. Keeping the magnitude is the orthogonal projection. If you change the magnitude a little bit more, then the distance between y prime and y will be even more than that. So while answering question, you have to tell me that if this one is not y, but it is equal to y plus some epsilon, then you have to show me that then the distance between y prime and y will be larger if epsilon is not 0. You have to show me that. That's unfortunately mathematics. And clearly enough, since we have only finite amount of duration for the lectures, I'm not doing this, but I will ask you to do it to show that this is the orthogonal projection with the minimum distance making between your starting point and the convex set here. It's the projection to the boundary of the set. And that projection is this one I'm showing you. You will have to prove it if I ask. Unfortunately, I'm not proving. I'm just explaining that this is the case. Now this one, yeah, is one methodology. The second alternative example where POCs can be used is called a filter design, and a filter design runs like this. I will very quickly go through this one, and I will direct you to a paper. I will indicate that. You want to design a filter, a low-pass filter, let's say, where this is the passband tolerance, and this is a cutoff frequency omega c. This is minus omega c, of course. And in the stop band, from omega c to pi, it's a discrete time filter. Therefore, it's from minus pi to pi. This is minus pi. This is this point is omega c prime. Okay, a different cutoff frequency. So in between, this is a delta ripple tolerance. This tolerance is, let's say, epsilon. So delta and epsilon is given to you, and from omega c to omega c prime, this region is called don't care region. So we don't care about what is the value of the filter magnitude response between omega c and omega c prime. Before omega c, it must be the passing low pass region, which is around 1. Okay, 1 minus delta over 2 to 1 plus delta over 2 kind of thing is necessary. And after omega c prime, it must be less than epsilon over 2 in magnitude. Okay, the filter response. So it must be stopping high frequencies. This is a low pass filter. H of the j omega. The way to do this with projections onto convex sets is by a few constraints. The constraint is, the first constraint is this in the frequency domain. The other constraint, call this constraint 1. The other one, second constraint, is number of filter tabs is capital N. So it must be, let's say, I don't know, 11 tab filter. An 11 tab filter is your constraint. You cannot have a longer filter, but it must have this kind of a thing. So you start with a random 11 tab arbitrary filter coefficient thing. You take the Fourier transform and project it onto this constraint. How do you do that? If the filter response is greater than 1 or less than, greater than 1 plus delta and less than 1 minus delta within the pass range, you clip them and force the frequency response to be around 1, between minus omega c and plus omega c. And if it is greater than omega c prime, it must be small. So you chop off everything which is above, let's say, epsilon over 2. So you, with scissors, you crop your Fourier transform, frequency response. And you now have a different Fourier transform. You take the inverse Fourier transform of it in, I don't know, 1000 point inverse FFT. And when you do that inverse FFT, you see that your new filter will consist of hundreds of or thousands of coefficients. However, it must be only 11 tab. So you crop only the central 11 tabs, crop off all the other ones, make them 0, and then take the Fourier transform again. Here you will see that they again go beyond these limits. So you push them to those limits by cropping with scissors. You take the inverse Fourier transform again. You look at it and you notice that beyond 11, there are still some non-zero values. You crop them again. You take the Fourier transform, crop in the Fourier domain, take the inverse transform, crop in the time domain beyond 11. After some time, you notice that the values beyond 11 tabs become smaller and smaller and smaller. They converge to 0. Or if it is good enough, you just stop the iteration over there. And meanwhile, when you take the Fourier transform, you notice that every time the Fourier transform fits better and better within these ranges, and you don't need to crop them anymore, any further. So that's the place where you need to stop the iteration. All right. And I have the software to do this. And I will share the software with you on the Canvas system on Mergen, so you can download the MATLAB codes of this one. I will show you. It's a very self-explanatory software, so if you just look at the help of it or look at the insight about how to use it, some example uses will also be given to you. Please do run them. And when you run them, you will see that it converges to the filter that we're looking for. So this will not be your exam question then. I will either ask the previous question or I will invent another question to require projections onto convex sets. But for this filter design, I will give you the software. And meanwhile, you can always you can also check the paper related to this one, which was authored by my supervisor, Enis Çetin, and me, and I think Yasemin Yardımcı Çetin. I'm not sure whether her surname was Yardımcı or Çetin then, because they are married with Enis Hoca. But it was a little bit long time ago. Yeah, probably it was Yasemin Yardımcı Çetin on Signal Processing Magazine. You can search for it, or you can search for my papers and look at some old ones, which is from the Signal Processing Magazine. Over there, you will find this paper. And I strongly recommend that you read it, because it's also giving you ideas that actually we can design filters even in 2 dimensions. So 2-dimensional filter design is also possible for this one. But the software is not provided with the paper. I will deliberately give the 1-dimensional software for this design on the canvas. But do not sell it or do not distribute it. It's just for your own research purposes, as an example. Okay, it's my property. That software is my property essentially. So that concludes today's lecture. It's already past 12 o'clock. We will continue with morphological operations and all those things starting next week. And it will be probably the final week of lectures. And then you will start presenting your presentations, your project presentations. Have you done them? Let's talk about it after I stop the recording.